What is going on, everybody? Welcome back to the Blackboard. We are going to continue off from our lecture of linear transformations by doing a set of examples. And so we're gonna start off with something like, very basic, slowly getting into it and instead of like just jumping all in. uh so we're gonna start with like, the small things, making sure that you have the vocabulary noted and you're able to figure out what it means when certain words are in the problem. So yeah, let's just get right into it. So we are given a vector v1 v2 in R2, and we're gonna let the linear transformation from R2 to R2 be defined as t v1 v2 is equal to v1 minus v2, and then the other corner will be v1 plus 2v2. And so now we are told to find the image of v is equal to negative 1, 2. Now, if you recall from the lecture on linear transformations, we know that there is a linear transformation from vector space V to W such that we have T, or the linear combination of T, which is B, W, and we also know that this is the image and this is the pre-image, which makes sense. Like the pre-image is like, kind of like the schematics, and we use that to get the actual final product, which would be our W, or the image. Before image, pre-image. So we are given the schematic of v negative 1, 2, and we are told using this schematic and this set of instructions that we were given to find the image. And so this this example is just pretty much like plug and chug. There's nothing hard about it. The only like hard quote unquote part is knowing what your image is, which would be our W. So all we really have to do is just plug in this v vector into our linear transformation. So our answer is going to be t negative 1, 2 is going to be so our v, this is our v1, this is our v2. So this is going to be negative 1, not comma, it's minus. Negative 1 minus 2, and then negative 1 plus 2 times 2. And we are left with negative 1 minus 2 is negative 3. And then 2 times 2 is 4, minus 1 is 3. So that is our W vector. So cool. That was pretty simple. So now part B is asked find the pre-image of negative 1, 11. So like as I mentioned before, the pre-image would be our schematic and our image is our final product. So because they are telling us to find a pre-image, then that means this, at this point it's not schematic. This vector here is our final product, which is our W. And so from here we just work it backwards. So instead of going a given vector, put it into the function and gives out the image, we have to take the image, undo the function to get us the original, or not the original, the pre-image, or the pre-outlined schematic, their draft. So raw materials. So it's just gonna pick a different color, and so we're just gonna undo this part. So we know that our function is given by this v1 minus v2 would be our first point, and then v1 plus 2v2 would be our second point. So this is going to be our w1, w2. So we know our w1 is going to be equal to v1 minus v2. So we're just going to plug in or substitute in the variables. We have negative 1 is equal to v1 minus v2. So we can't do much here, so we're just going to move on with the next one. The other one is W2 is equal to V1 plus 2V2. And so again, I'm just going to plug is equal to 11. And that is V1 plus 2V2. Cool. We got two equations, two unknowns. What does that mean? A, we could use systems of equations to solve this. We could, but I mean we can just substitute, because we can find that here V1 is equal to V2 minus 1, and so we're just gonna plug that in here. So this is equal to V2 minus 1 plus 2V2, and so we're just gonna move this one to the 11 here, so we're gonna add both sides by 1. So we have 12 is equal to V2 plus 2V2 is 3V2, so V2 is equal to 4, so that means V1 is equal to 4 minus 1 is 3. And so our pre-image is going to be, it's supposed to be an equal sign, it's going to be 3, because that's our V1, 4. and then that's our answer. So that's the answer for the part B, and then this is the answer for part A. So we were given this function that has let us take a vector and convert it to another vector or its image. But how do we know that this is a linear transformation? Well, I mean, just go ahead and do part C that I was hiding over here all along. Ha ha ha. And so now we have to show that this linear transformation, or that this transformation is a linear transformation from R2 to R2. And as you know, you've done this with subspaces. You've done it with subspaces. What else have you done it? I feel like you've done it with other things, but for sure you've done it with subspaces. We got to do them again. We got to show that this linear transformation is closed under addition and closed under scalar multiplication. And let's get right to it. We have to go do this again. So, pick a different color. I don't know. Let's do this one. So, first, we're going to show that it's closed under addition. We're going to be using two arbitrary vectors, u plus v. And so we know that this is equal to u1 plus u2 plus v1 plus v2. And you can add two coordinates or 2 points together. So this will simply be u1 plus v1, then and it's going to be u2 plus v2. Cool. So now let's just plug this into our linear transformation. u1 plus v1, and then comma u2 plus v2. And so this is going to put in this function, and so this is going to be put in parentheses u1 plus v1 minus u2 plus v2 on a parentheses, and then here we have u1 plus v1 plus 2 times u1 plus, not u1, it's u2 plus v2. Cool. So here's what we can do now. Because addition in general, it's commutative, we can put these two together and put these two together. Same thing goes with the other one. You can put these u's together, you know, combining, I want to say like terms, but like combining similar terms. And so we now have u1 minus u2 plus v1 minus v2. This is a v. And then over here we have u1 plus 2u2 plus v1 plus 2v2. And hello, yo, this looks kind of look familiar. So let's break this up one more time, Again, we're just going to put in the u's on one side and then the v's on the other. And so we are left with u1 minus u2 comma u1 plus 2u2 plus, because we can do this, v1 minus v2, it's a 1, and then v1 plus 2v2. Hey, yo, what do we got here? We got, yo, this part looks very, I should probably use a different color. This part looks very similar to what we have as our function. Same thing goes with the other one. This looks like this. So we can say that this is t of u1 u2 plus t of v1 v2, which is t of u vector plus t of v. So this is close under addition. This is the same as that's what we have here. Yo, that's cool. All right, so what about multiplication? Well, you could do the same thing again. This time do a darker shade. Wait, I wonder if purple can y'all see this? I think y'all can. I hope y'all can. So let's do close under scalar. I can't spell scalar. Scalar multiplication. That's a U. So if we have some constant c, we multiply it by the vector u. This is going to be c times u1 u2, which we can put the constant inside, so we have u1 plus cu2. All right, cool. So now we're just gonna plug this into our little function transformation thing. What are we doing? cu1, not good job, genius. It's not a plus, it's a comma. The comma cu1 cu2. So this is gonna be equal to was it 1 minus 2? Okay, so this is gonna be cu1 minus cu2, and then our next point is gonna be cu1 plus 2cu2. We can factor out the c's, so we have c of u1 minus u2, and then cu1 plus u2, and then we can factor out the c again, so we're left with c. Oh, that is way too big. Factor it out one more time. You have c u1 minus u2, then u1 plus 2u2, and lo and behold, this is our what's it called? Our function thing. I don't know. So this is the same thing as c times t u1 u2, or c times t of vector u. So this is also closed under scalar multiplication. Therefore, t is a linear transformation. I don't even know if spelling is right. So we just show that this is a linear transformation, and that's pretty much it for this video. I might do like a couple more of image pre-image, and then after that I'm gonna start throwing in a bunch of functions, and we have to show that it is or it isn't a linear transformation. So I might do a couple more examples on images and pre-images, but I think for the rest of the examples, it will focus on showing that something is or isn't a linear transformation. So for this one, I just wanted to put 2 in 1 because it's like find the image and pre-image, but we also show that this is going to be a linear transformation. So yeah, hopefully this helped you out a good bit. If not, that's okay. Like I mentioned, I'm gonna find more examples, and then from there just gonna kind of like go from like, little bit harder, 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 and we'll we'll see. Hopefully that this helps. But yeah, I'll see you guys in the next video.